The lightweight directory access protocol is an open, vendor-neutral, industry-standard application protocol for accessing and maintaining distributed directory information services over an Internet protocol network. Directory services play an important role in developing intranet and Internet applications by allowing the sharing of information about users, systems, networks, services, and applications throughout the network. As examples, directory services may provide any organized set of records, often with a hierarchical structure, such as a corporate email directory. Similarly, a telephone directory is a list of subscribers with an address and a phone number. LDAP is specified in a series of Internet Engineering Task Force standard track publications called Request for Comments, using the description language ASN1. The latest specification is version 3, published as RFC 4511. For example, here is an LDAP search translated into plain English: search in the company email directory for all people located in Nashville whose name contains Jesse that have an email address. Please return their full name, email, title, and description. A common usage of LDAP is to provide a single sign-on, where one password for a user is shared between many services, such as applying a company login code to web pages. LDAP is based on a simpler subset of the standards contained within the X500 standard. Because of this relationship, LDAP is sometimes called X500 Lite. History: telecommunication companies' understanding of directory requirements was well developed after some 70 years of producing and managing telephone directories. These companies introduced the concept of directory services to information technology and computer networking, their input culminating in the comprehensive X500 specification, a suite of protocols produced by the International Telecommunication Union in the 1980s. X500 directory services were traditionally accessed via the X500 Directory Access Protocol, which required the Open Systems Interconnection Protocol stack. LDAP was originally intended to be a lightweight alternative protocol for accessing X500 directory services through the simpler TCP/IP protocol stack. This model of directory access was borrowed from the Dixie and Directory Assistance Service protocols. Standalone LDAP directory servers soon followed, as did directory servers supporting both DAP and LDAP. The latter has become popular in enterprises, as LDAP removed any need to deploy an OSI network. Today, X500 directory protocols including DAP can also be used directly over TCP/IP. The protocol was originally created by Tim Howes of the University of Michigan, Steve Kill of ISOD Limited, Colin Robbins of Nexa and Weng-Yik Young of Performance Systems International, circa 1993. Mark Wall of Critical Angle Incorporated, Tim Howes, and Steve Kill started work in 1996 on a new version of LDAP, LDAP v3, under the aegis of the Internet Engineering Task Force. LDAP v3, first published in 1997, superseded LDAP v2 and added support for extensibility, integrated the simple authentication and security layer, and better aligned the protocol to the 1993 edition of X500. Further development of the LDAP v3 specifications themselves and of numerous extensions adding features to LDAP v3 has come through the IETF. In the early engineering stages of LDAP, it was known as Lightweight Directory Browsing Protocol, or LDBP. It was renamed with the expansion of the scope of the protocol beyond directory browsing and searching, to include directory update functions. It was given its lightweight name because it was not as network-intensive as its DAP predecessor and thus was more easily implemented over the Internet due to its relatively modest bandwidth usage. LDAP has influenced subsequent Internet protocols, including later versions of X500, XML-enabled directory, directory service markup language, service provisioning markup language, and the service location protocol. Protocol overview: a client starts an LDAP session by connecting to an LDAP server, called a directory system agent, by default on TCP port and UDP port 389. The client then sends an operation request to the server, and the server sends responses in return. With some exceptions, the client does not need to wait for a response before sending the next request, and the server may send the responses in any order. All information is transmitted using basic encoding rules. The client may request the following operations: start TLS use the LDAP-v3 transport layer security extension for a secure connection, bind authenticate and specify LDAP protocol version, search search for and/or retrieve directory entries, compare test if a named entry contains a given attribute value, add a new entry, delete an entry, modify an entry, modify distinguish name move or rename an entry, abandon abort a previous request, extended operation generic operation used to define other operations, unbind close the connection. In addition, the server may send unsolicited notifications that are not responses to any request, for example before the connection is timed out. A common alternative method of securing LDAP communication is using an Ssl tunnel. This is denoted in LDAP URLs by using the URL scheme LDAPS. The default port for LDAP over SSL is 636. The use of LDAP over SSL was common in LDAP version 2, but it was never standardized in any formal specification. This usage has been deprecated along with LDAP v2, which was officially retired in 2003. Directory structure. The protocol provides an interface with directories that follow the 1993 edition of the X500 model. An entry consists of a set of attributes. An attribute is a name and one or more values. The attributes are defined in a schema. Each entry has a unique identifier, its distinguished name. This consists of its relative distinguished name, constructed from some attribute, S, in the entry, followed by the parent entry's DN. Think of the DN as the full file path and the RDN as its relative file name in its parent folder. A DN may change over the lifetime of the entry, for instance, when entries are moved within a tree. To reliably and unambiguously identify entries, a UUID might be provided in the set of the entry's operational attributes. An entry can look like this when represented in LDAP data interchange format. DN, CN equals John Doe, DC equals example, DC equals com, CN, John Doe, given name, John, SN, Doe, telephone number, +1, 888, 555, 6789, telephone number, +1, 888, 555, 1232, mail, john@example.com, manager, CN equals Barbara Doe, DC equals example, DC equals com, object class, inet.org person, object class, organizational person, object class, person, object class, top. DN is the distinguished name of the entry. It is neither an attribute nor a part of the entry. CN equals John Doe is the entry's RDN, and DC equals example, DC equals com is the DN of the parent entry, where DC denotes domain component. The other lines show the attributes in the entry. Attribute names are typically mnemonic strings, like CN for common name, DC for domain component, mail for email address, and SN for surname. A server holds a subtree starting from a specific entry, for example DC equals example, DC equals com, and its children. Servers may also hold references to other servers, so an attempt to access U equals department, DC equals example, DC equals com could return a referral or continuation reference to a server that holds that part of the directory tree. The client can then contact the other server. Some servers also support chaining, which means the server contacts the other server and returns the results to the client. LDAP rarely defines any ordering. The server may return the values of an attribute, the attributes in an entry, and the entries found by a search operation in any order. This follows from the formal definitions. An entry is defined as a set of attributes, and an attribute is a set of values, and sets need not be ordered. Operations. Add. The ADD operation inserts a new entry into the directory server database. If the distinguished name in the add request already exists in the directory, then the server will not add a duplicate entry but will set the result code in the add result to decimal 68. Entry already exists. LDAP compliance servers will never dereference the distinguished name transmitted in the add request when attempting to locate the entry, that is, distinguished names are never de-aliased. LDAP compliance servers will ensure that the distinguished name and all attributes conform to naming standards, the entry to be added must not exist, and the immediate superior must exist. DN, with equals user, U equals people, DC equals example, DC equals com, shiny type, add, object class, top, object class, person, WID, user, SN, last name, CN, common name, user password, password. In the above example, with equals user, U equals people, DC equals example, DC equals com must not exist, and U equals people, DC equals example, DC equals com must exist. Bind. When an LDAP session is created, that is, when an LDAP client connects to the server, the authentication state of the session is set to anonymous. The bind operation establishes the authentication state for a session. Simple bind and SASL plain can send the user's DN and password in plain text, so the connections utilizing either simple or SASL plain should be encrypted using transport layer security. The server typically checks the password against the user password attributes in the named entry. Anonymous bind resets the connection to anonymous state. Ssl bind provides authentication services through a wide range of mechanisms, for example Kerberos or the client certificate sent with TLS. Bind also sets the LDAP protocol version. The version is an integer and at present must be either 2 or 3, although the standard supports integers between 1 and 127 in the protocol. If the client requests a version that the server does not support, the server must set the result code in the bind response to the code for a protocol error. Normally clients should use LDAP v3, which is the default in the protocol but not always in LDAP libraries. Bind had to be the first operation in a session in LDAP v2, but is not required in LDAP v3. In LDAP v3, each successful bind request changes the authentication state of the session and each unsuccessful bind request resets the authentication state of the session. Delete. To delete an entry, an LDAP client transmits a properly formed delete request to the server. A delete request must contain the distinguished name of the entry to be deleted. Request controls may also be attached to the delete request. Servers do not dereference aliases when processing a delete request. Only leaf entries may be deleted by a delete request. Some servers support an operational attribute as subordinates whose value indicates whether an entry has any subordinate entries, and some servers support an operational attribute num subordinates indicating the number of entries subordinate to the entry containing the num subordinates attribute. Some servers support the subtree delete request control permitting deletion of the DN and all objects subordinate to the DN, subject to access controls. Delete requests are subject to access controls, that is, whether a connection with a given authentication state will be permitted to delete a given entry is governed by server-specific access control mechanisms. Search and compare. The search operation is used to both search for and read entries. Its parameters are, base objector, the name of the base object entry relative to which the search is to be performed, scopeer, what elements below the base object to search. This can be base object, single level, or whole subtree, filterer, criteria to use in selecting elements within scope. For example, the filter, given name equals John, male equals John will select persons, where the matching rules for given name and male determine whether the values for those attributes match the filter assertion. Note that a common misconception is that LDAP data is case-insensitive, whereas in fact matching rules and ordering rules determine matching, comparisons, and relative value relationships. If the example filters were required to match the case of the attribute value, an extensible match filter must be used, for example, given name, case exact match equals John, male, case exact substrings match, equals John, Derivaliases, whether and how to follow alias entries. Attributes, which attributes to return and result entries. Size limit, time limiter, maximum number of entries to return, and maximum time to allow search to run. These values, however, cannot override any restrictions the server places on size limit and time limit. Types only, return attribute types only, not attribute values. The server returns the matching entries and potentially continuation references. These may be returned in any order. The final result will include the result code. The compare operation takes a DN, an attribute name and an attribute value, and checks if the named entry contains that attribute with that value. Modify. The modify operation is used by LDAP clients to request that the LDAP server make changes to existing entries. Attempts to modify entries that do not exist will fail. Modify requests are subject to access controls as implemented by the server. The modify operation requires that the distinguished name of the entry be specified, and a sequence of changes. Each change in the sequence must be one of add, delete, replace, LDIF example of adding a value to an attribute. DN, DC equals example, DC equals com, Shani type, modify, add, CN, CN, the new CN value to be added. To replace the value of an existing attribute, use the replace keyword. If the attribute is multi-valued, the client must specify the value of the attribute to delete. To delete an attribute from an entry, use the keyword delete and the Shani type designator modify. If the attribute is multi-valued, the client must specify the value of the attribute to delete. There is also a modify increment extension which allows an incrementable attribute value to be incremented by a specified amount. The modify increment extension uses Object Identifier 1.3.6.1.1.14. The following example using LDIF increments employee number by 5. DN, with equals user 0, U equals people, DC equals example, DC equals com, Shani type, modify, increment, employee number, 5. When LDAP servers are in a replicated topology, LDAP clients should consider using the post-read control to verify updates instead of a search after an update. The post-read control is designed so that applications need not issue a search request after an update. It is bad form to retrieve an entry for the sole purpose of checking that an update worked because of the replication eventual consistency model. An LDAP client should not assume that it connects to the same directory server for each request because architects may have placed load balancers or LDAP proxies or both between LDAP clients and servers. Modify DN. Modify DN takes the new RDN, optionally the new parent's DN, and a flag that says whether to delete the value, S, in the entry that match the old RDN. The server may support renaming of entire directory subtrees. An update operation is atomic, other operations will see either the new entry or the old one. On the other hand, LDAP does not define transactions of multiple operations. If you read an entry and then modify it, another client may have updated the entry in the meantime. Servers may implement extensions that support this, though. Extended operations. The extended operation is a generic LDAP operation that can define new operations that were not part of the original protocol specification. StarTLS is one of the most significant extensions. Other examples include cancel and password modify. StarTLS. The StarTLS operation establishes transport layer security on the connection. It can provide data confidentiality and/or data integrity protection. During TLS negotiation, the server sends its X509 certificate to prove its identity. The client may also send a certificate to prove its identity. After doing so, the client may then use Ssl External. By using the Ssl External, the client requests the server derive its identity from credentials provided at a lower level. Though technically the server may use any identity information established at any lower level, typically the server will use the identity information established by TLS. Servers also often support the non-standard LDAPS protocol on a separate port, by default 636. LDAPS differs from LDAP in two ways. 1. Upon connect, the client and server establish TLS before any LDAP messages are transferred, and 2. The LDAPS connection must be closed upon TLS closure. It should be noted that some LDAPS client libraries only encrypt communication, they do not check the host name against the name in the supplied certificate. Abandon. The abandon operation requests that the server abort an operation named by a message ID. The server need not honor the request. Neither abandon nor a successfully abandoned operation send a response. A similar cancel extended operation does send responses, but not all implementations support this. Unbind. The unbind operation abandons any outstanding operations and closes the connection. It has no response. The name is of historical origin, and is not the opposite of the bind operation. Clients can abort a session by simply closing the connection, but they should use unbind. Unbind allows the server to gracefully close the connection and free resources that it would otherwise keep for some time until discovering the client had abandoned the connection. It also instructs the server to cancel operations that can be cancelled, and to not send responses for operations that cannot be cancelled. LDAP URLs. An LDAP URL format exists, which clients support in varying degrees, and servers return in referrals and continuation references. LDAP, host port DN. Attributes. Scope. Filter. Extensions. Most of the components described below are optional. Host is the FQDN or IP address of the LDAP server to search. Port is the network port of the LDAP server. DN is the distinguished name to use as the search base. Attributes is a comma-separated list of attributes to retrieve. Scope specifies the search scope and can be base, 1, or sub. Filter is a search filter. For example, as defined in RFC 4515. Extensions are extensions to the LDAP URL format. For example, LDAP, ldap.example.com/ cn equal John%20do, dc equal example, dc equal com refers to all user attributes in John Doe's entry in ldap.example.com, while ldap/dc equals example, dc equals com. Sub. Given name equals John, searches for the entry in the default server. As in other URLs, special characters must be %encoded. There is a similar non-standard LDAPS URL scheme for LDAP over SSL. This should not be confused with LDAP with TLS, which is achieved using the start TLS operation using the standard LDAP scheme. Schema. The contents of the entries in a subtree are governed by a directory schema, a set of definitions and constraints concerning the structure of the directory information tree. The schema of a directory server defines a set of rules that govern the kinds of information that the server can hold. It has a number of elements, including attributes. Syntaxes provide information about the kind of information that can be stored in an attribute. Matching rules provide information about how to make comparisons against attribute values. Matching rule uses indicate which attribute types may be used in conjunction with a particular matching rule. Attribute type is define an object identifier and a set of names that may be used to refer to a given attribute, and associates that attribute with a syntax and set of matching rules. Object classes define named collections of attributes and classify them into sets of required and optional attributes. Name forms define rules for the set of attributes that should be included in the RDN for an entry. Content rules define additional constraints about the object classes and attributes that may be used in conjunction with an entry. Structure rules define rules that govern the kinds of subordinate entries that a given entry may have. Attributes are the elements responsible for storing information in a directory, and the schema defines the rules for which attributes may be used in an entry, the kinds of values that those attributes may have, and how clients may interact with those values. clients may learn about the schema elements that the server supports by retrieving an appropriate subschema subentry. The schema defines object classes. Each entry must have an object class attribute, containing named classes defined in the schema. The schema definition of the classes of an entry defines what kind of object the entry may represent, for example a person, organization or domain. The object class definitions also define the list of attributes that must contain values and the list of attributes which may contain values. For example, an entry representing a person might belong to the classes top and person. Membership in the person class would require the entry to contain the SN and CN attributes, and allow the entry also to contain user password, telephone number, and other attributes. Since entries may have multiple object classes values, each entry has a complex of optional and mandatory attribute sets formed from the union of the object classes it represents. Object classes can be inherited, and a single entry can have multiple object classes values that define the available and required attributes of the entry itself. A parallel to the schema of an object class is a class definition and an instance in object-oriented programming, representing LDAP object class and LDAP entry, respectively. Directory servers may publish the directory schema controlling an entry at a base DN given by the entry's sub-MA subentry operational attribute. Server administrators can add additional schema entries in addition to the provided schema elements. A schema for representing individual people within organizations is termed a white pages schema. Variations: a lot of the server operation is left to the implementer or administrator to decide. Accordingly, servers may be set up to support a wide variety of scenarios. For example, data storage in the server is not specified, the server may use flat files, databases, or just be a gateway to some other server. Access control is not standardized, though there has been work on it and there are commonly used models. Users' passwords may be stored in their entries or elsewhere. The server may refuse to perform operations when it wishes, and impose various limits. Most parts of LDAP are extensible. Examples: one can define new operations. Controls may modify requests and responses, for example to request sorted search results. New search scopes and bind methods can be defined. Attributes can have options that may modify their semantics. Other data models: as LDAP has gained momentum, vendors have provided it as an access protocol to other services. The implementation then recasts the data to mimic the LDAP X500 model, but how closely this model is followed varies. For example, there is software to access SQL databases through LDAP, even though LDAP does not readily lend itself to this. X500 servers may support LDAP as well. Similarly, data previously held in other types of data stores are sometimes moved to LDAP directories. For example, Unix user and group information can be stored in LDAP and accessed via PAM and NSS modules. LDAP is often used by other services for authentication. An example of such data model is the glue schema, which is used in a distributed information system based on LDAP that enable users, applications and services to discover which services exist in a grid infrastructure and further information about their structure and state. Usage: an LDAP server may return referrals to other servers for requests that it cannot fulfill itself. This requires a naming structure for LDAP entries so one can find a server holding a given distinguished name, a concept to find in the X500 directory and also used in LDAP. Another way of locating LDAP servers for an organization is a DNS server record. An organization with the domain example.org may use the top-level LDAP DNDC equals example, DC equals org. If the LDAP server is also named ldap.example.org, the organization's top-level LDAP URL becomes ldap, ldap.example.org/. DC equal example, DC equal org. Primarily two common styles of naming are used in both X500, 2008, and LDAP v3. These are documented in the ITU specifications and IETF RFCs. The original form takes the top-level object as the country object, such as C equals US, C equals FR. The domain component model uses the model described above. An example of country-based naming could be L equals locality, U equals some organizational unit, O equals some organization, C equals FR, or in the US, CN equals common name, L equals locality, U equals some organizational unit, O equals some organization, ST equals CA, C equals US. See also, Federated Naming Service, Global Directory Server, HISID, Hierarchical Database Model, Key Server, LDAP Application Program Interface, List of LDAP software, Simple Authentication and Security Layer, Ambiguous Name Resolution, References. Notes, ITUT Rec. X680, Abstract Syntax Notation 1, Specification of Basic Notation, 1994, Basic Encoding Rules, ITUT Rec. X690, Specification of ASN1 Encoding Rules, Basic, Canonical, and Distinguished Encoding Rules, 1994, RFC 3641, Generic String Encoding Rules for ASN1 Types, RFC 4346, the TLS Protocol version 1.1, RFC 4422, Simple Authentication and Security Layer, SASL Mechanisms registered at IANA. This article is based on material taken from the Free Online Dictionary of Computing prior to November 1, 2008 and incorporated under the relicensing terms of the GFDL, version 1.3 or later. Further reading, Archils, BLDAP Directories Explained, An Introduction and Analysis. Addison Wesley Professional. ISBN A0-201-78792 Carter, GLDAP System Administration O'Reilly Media. ISBN A1-56592-491-6 Donnelly, CLDAP Programming, Management, and Integration. Manning Publications. ISBN A1-930110-40-5 House, T. Smith, M. Good, G. Understanding and Deploying LDAP Directory Services. Addison Wesley Professional. ISBN A0-672-32316-8 Rotom, J. Programmer's Guide to Internet Mail, SMTP, POP, IMAP, and LDAP. Elsevier. ISBN A1-55558-212-5 Vogelmeyer, Are the ABCs of LDAP, How to Install, Run, and Administer LDAP Services. Auerbach Publications. ISBN A0-8493-1346-5 External links, devsh.com, Understanding LDAP, a simple, light introductory tutorial for LDAP. Skills-.cook, LDAP Schema Design, capitalhead.com, Troubleshooting LDAP SSL connection issues between Microsoft ILM-MIS and Novell Directory 8.7.3, Prasinatech.com, LDAP Schema Design, a case study, LDAP Esoterica, Deep Dive LDAP Esoterica, RFCs. LDAP is specified in a series of request for comments documents, RFC 4510, LDAP, Technical Specification Roadmap, RFC 4511, LDAP, the Protocol, RFC 4512, LDAP, Directory Information Models, RFC 4513, LDAP, Authentication Methods and Security Mechanisms, RFC 4514, LDAP, String Representation of Distinguished Names, RFC 4515, LDAP, String Representation of Search Filters, RFC 4516, LDAP, Uniform Resource Locator, RFC 4517, LDAP, Syntaxes and Matching Rules, RFC 4518, LDAP, Internationalized String Preparation, RFC 4519, LDAP, Schema for User Applications. The following RFCs detail LDAP-specific best current practices. RFC 4520, Internet Assigned Numbers Authority Considerations for the Lightweight Directory Access Protocol. RFC 4521, Considerations for Lightweight Directory Access Protocol Extensions. The following is a partial list of RFCs specifying LDAP v3 extensions. RFC 2247, Use of DNS Domains. In distinguished names, RFC 2307, Using LDAP as a Network Information Service. RFC 2589, LDAP v3, Dynamic Directory Services Extensions. RFC 2649, LDAP v3 Operational Signatures. RFC 2696, LDAP Simple Paged Result Control. RFC 2798, INET.org Person LDAP Object Class. RFC 2830, LDAP v3, Extension for Transport Layer Security. RFC 2849, the LDAP Data Interchange Format. RFC 2891, Server-Side Sorting of Search Results. RFC 3045, Storing Vendor Information in the LDAP Root DSE. RFC 3062, LDAP Password Modify Extended Operation. RFC 3296, Name Subordinate References in LDAP Directories. RFC 3671, Collective Attributes in LDAP. RFC 3672, Subentries in LDAP. RFC 3673, LDAP v3, All Operational Attributes. RFC 3687, LDAP Component Matching Rules. RFC 3698, LDAP, Additional Matching Rules. RFC 3829, LDAP Authorization Identity Controls. RFC 3866, Language Tags and Ranges in LDAP. RFC 3909, LDAP Cancel Operation. RFC 3928, LDAP Client Update Protocol. RFC 4370, LDAP Proxied Authorization Control. RFC 4373, LBURP. RFC 4403, LDAP Schema for UDDI. RFC 4522, LDAP, Binary Encoding Option. RFC 4523, LDAP, X509 Certificate Schema. RFC 4524, LDAP, Cosigned Schema. RFC 4525, LDAP, Modify Increment Extension. RFC 4526, LDAP, Absolute True and False Filters. RFC 4527, LDAP, Read Entry Controls. RFC 4528, LDAP, Assertion Control. RFC 4529, LDAP, Requesting Attributes by Object Class. RFC 4530, LDAP, Entry UID. RFC 4531, LDAP Turn Operation. RFC 4532, LDAP Who Am I? Operation. RFC 4533, LDAP Content Sync Operation. RFC 4876, Configuration Profile Schema for LDAP-based agents. RFC 5020, LDAP Entry DN Operational Attribute. LDAP v2 was specified in the following RFCs. RFC 1777, Lightweight Directory Access Protocol. RFC 1778, the String Representation of Standard Attributes Syntaxes. RFC 1779, a String Representation of Distinguished Names. LDAP v2 was moved to historic status by the following RFC. RFC 3494, Lightweight Directory Access Protocol version 2 to historic status.